Hey Chan Physics, Mr. Block, just doing a quick video just in case you missed class or wanted to review it again. Newton's third law, okay? And remember Newton's third law, we often always remember it as every action has an equal and opposite reaction. And if we do that, we're going to be inaccurate, okay? It's not going to be right. So let's take a look at what the actual is. The actual law is every action force has an equal and opposite reaction force. We're gonna focus today a real short video on why it is that the word force is really important to start remembering when we think about Newton's third law. All right, so remember that Newton's third law describes what happens when two things push or pull on each other. The actual law is every action force has an equal and opposite reaction force. And so what you should remember is that whenever we see two things, that will give us an idea. Oh, we're not talking about maybe Newton's second law, F equals ma, but we're thinking about Newton's third law. Every action force has an equal and opposite reaction force. So there'll be two objects. Those two forces will be the same and in opposite directions. And I'm going to teach you real quick how to identify those forces. But first, let's figure out what we mean by the difference between the forces are equal and opposite, but the effects are different. So here's our example. We got an elephant and Newton standing on skateboards. And they're going to put their trunk and hands together. And the elephant is going to push on Newton. Okay, that's what we'll call the action force. That's the thing that's pushing. Immediately upon the elephant starting to push on Newton, Newton's third law says that an equal and opposite reaction force will push on the elephant from Newton. So there's an action force right in the middle there, the elephant pushing on Newton, the reaction force equal and opposite, right? Because we can see it, they're the same size, Newton pushing back on the elephant. Okay, so those are the forces, and those are equal. We can see them like the red arrows, they're equal, they're the same size. But the effect, okay, of those two forces is going to be quite different. The elephant has a huge inertia, a huge amount of mass, and so even though this force is equal to the action force, right, it's going to mean that the elephant's going to move slowly backwards. Whereas this force right here, the one that's pushing on Newton, well, Newton is pretty skinny in this picture, and so we see that Newton is going to move back quickly. All right, so these are not equal, right? The effects of what's happening is not equal, but the forces are equal. So we're going to focus on trying to make sure that we understand that difference and that we can always identify where the forces are. All right, so here's real quick a summary of what I just tried to tell you. Action and reaction forces are pushes. They're not movements, right? So don't look at action or reaction as anything but forces. Always between two objects in contact. They are the same size. And then this is important. They don't cancel each other, right? So even though we have two forces that are equal and they're going in opposite direction, because we have two objects, well, this force is going to go on this object, and this force is going to go on this object. And so they don't cancel like they would if this was one object with the two forces like we have been doing in the past, right? And equal two forces on one object will cancel each other. But in Newton's third law, we have two objects, and so they don't cancel each other. All right? We want to make sure that you understand that action and reaction forces don't equal cause and effect, right? So in our example, the elephant moves back slowly while Newton moves back very quickly. All right. And then you can read the rest of them. Effects can be different because of inertia. All right. So how will we go about doing this, right? How will we go about figuring out where the action and reaction forces is? So here's some examples. Forces always come in pairs. And we have a person, a student, who throws maybe a heavy ball like a bowling ball and sits on a skateboard, and there's nothing touching that person, right? But that person puts a force on the ball and throws the ball, and the person's going to move backwards, right? And so we see that action and reaction forces. The person pushes on the ball, ball goes that way, but the ball is going to push back on the person, and the person's going to move back. Okay. You can push on a wall, the wall will push back on you, right? As hard as you can push on the wall will push back just as hard. And then we can see here the beginnings of this is how we walk or we move on a skateboard, right? We actually use Newton's law every day when we walk, because what do? We push down on the floor at an angle. And what has happened? The floor pushes back on us. So let's take a look real quick at how we might test this or might assess this. So we have these three ideas right here. A bowling ball pushes on the pin, the earth pulls on you down, and the paddle pushes on the boat. And so let's take a look at whether or not we can figure out what is happening. And so what I want to teach you is that whenever you're asked to identify the different forces, all I really need for you guys to do is to find the spot where the two objects come together and draw a line. Boom, like this. Draw a line between them. All right. So then we know, right, Newton's third law, that this bowling ball is going to push on this pin. That's our action force. Our action force is going like this way. And then we should know that then from Newton's third law that every action force has an equal and opposite reaction force. And so we should see that force right there. So if we draw this line, we draw our action force, then we can know that our reaction force is equal and opposite. We'll do two more examples. So here we have the person pushing on the earth, right? Or the earth pulls down on you. So we'll draw a line between you and the earth. The earth is going to pull down on you. So there's our action force. And then what's our reaction force? Well, it's just going to be equal and opposite. And what is that? Well, that's you pulling back on the earth. All right. And then finally, paddling a boat. And this is one that I think that many of us haven't really thought about. Why does pulling backwards on a paddle push a boat forward? And now we can see from Newton's third law that this is actually what's happening. So if we draw a line between the paddle and the water, right, and we know that the paddle is pushing like this on the water, well, Newton's third law would say that there's an equal and opposite reaction force, the water pushing this way on the paddle and the person on the boat, propelling the boat forward. Okay, that's a simple way to learn Newton's third law. And in the co-formative that you're going to do real quick, you're going to see that we're just going to make sure that you can figure this out, and you can always use this system, right? Draw a line between where the two objects meet, draw the action force, and then draw an equal and opposite reaction force, and then evaluate what it means, okay? All right, I think that we are almost done. So I just wanted to show you real quickly, here is an example that we all used to play with of Newton's third law. A balloon, okay? And a balloon here, the air in the balloon is going to be rushing out. If we were to draw a line right here between where the balloon and the air, right? The air is going to push this way, right? Push this way. And what is the Newton's third law says? Well, then the air will then create a force this way that will actually push our balloon. Right? So do the real quick the couple questions that I have for you guys on Newton's third law, and then I'll introduce the Challenger disaster and why it is that we're watching.